I want to start with a question. Just how many of you saw Nick's presentation from yesterday on verification and getting the human out of the loop? And so that's roughly about 50% or so. So what you're going to see today sort of connects to that and builds on that. And maybe just as a quick refresher for those of you who are here and a primer for those of you who haven't yet seen that talk, he kind of distilled it down into one slide. At least he talked about a big picture of where we've been in SDN, where we are now, and what's coming over the next 10 years. And the work we're doing now and the presentations you're going to hear today really connect to that. So it's important to try to help connect the dots for everybody. So he looked backwards and pointed out that in phase 1 of SDN, network operators took control of the software of their network. Then in phase 2, in which we're in right now, network owners take control of packet processing. And then in phase 3, which we're leading into at this moment, the networks start to become manageable through a verifiable closed-loop control. And through this, we start to get humans out of the loop when we're controlling and running networks. So another way to look at this and put it in a little bit of more specific context for ONF is that, yes, we've been on this SDN journey. We started with a bold vision of separating the control and data planes, of centralized control, and of open flow. We all know these pieces, and it delivered certain benefits in simplified forwarding devices, faster innovation cycles, and reduced costs overall. And this SDN track has been quite successful. At this point now, we have open source SDN implementations that are in live production, and you're hearing about that here this week at ONF Connect. Well, two things have happened along the way. One is that some organizations, Google notably, took off with SDN and used it and leveraged it in new and innovative ways and have built networks at scale and proven the viability and value of SDN. But in parallel, the industry has actually done something that I call here SDN minus, which is actually to take the name SDN and sort of the premise, but actually use it to write software management tools on top of legacy devices that still use proprietary embedded routing protocols, for instance. So in terms of NIC's phase 2 is really these programmable technologies I've just animated up here, which is really programmable silicon, P4 runtime, and cloud dev models, DevOps and CI/CD, which I'm adding to the picture here, but that's a new technology that's new and notable and has really driven a tremendous transformation in our industry. And now we're entering phase 3. And phase 3 is built on these new technologies and also the lessons learned of the last decade, and delivering some notable leaps forward that are around top-down programmability, hardware independence, a cloud-like lifecycle, bringing cloud-like agility to the network for the first time, and verifiability. And this delivers a whole suite of new benefits that are quite substantial in terms of really giving the operator, for the first time, top-down control of the network, enabling rapid network innovation cycles, zero-touch operation, and importantly, a robust hardware ecosystem like we have not experienced in the past. So in terms of the stack that ONF is building, you're going to hear about that today. It's really built from the ground up on forwarding devices, both forwarding devices that support full programmability in terms of P4, and also fixed function and partially programmable devices. And it's important that we support that whole ecosystem of devices because that's really what enables this dynamic hardware ecosystem and also gives us a smooth migration path into the future. On top of that, Stratum, which you've been hearing about and has now been open sourced this week. We're really excited about that. This is a thin switch OS that supports all these next-gen SDN interfaces like P4 runtime, GNMI, and GNOI, northbound out of Stratum, and open config models. And MicroONOS, which is the SDN controller here that supports all these next-gen interfaces, as you might imagine, but more southbound, and a new config and management subsystem based on open config models. Importantly, it's based on cloud native, microservices, Kubernetes, gRPC, and the like. And it enables the apps that run on top of MicroONOS to take advantage of all this. So if you can program the silicon, it's important that the apps can come up with a new programming model, can actually push that all the way down to the silicon, and then can use and leverage that And so that's all part of this tool chain, is to be able to expose all this capability that's becoming available all the way up to the application developers for the very first time. So on top of this stack that we just described here, which is hardware, Stratum, and micro-ONO sitting on top of it, we're also adding this verification engine, this verification capability that Nick was talking about, we're going to talk about more here today, which is based first on the ability to do fine-grained measurement and to measure all packets and all flows in the network, and to be able to use that information to then be able to provide feedback and to be able to tune the network and respond to how the network is actually behaving in real time. And then on top of that, a whole set of tools to operationalize the network in a cloud-like way, to bring DevOps, to bring CI/CD for the very first time to the network. And what this really enables is, for a developer to be able to craft a feature and push it to the network, to the production network, and know that they can roll it back if it causes any problems. And not just they can roll it back, but in an automated way, the network can be monitored, and if the network's not behaving properly, the rollback will automatically take place. This enables then a new sense of comfort in terms of deploying new features, and that's what really drives innovation. If you can push new features, see how they're working, pull them back if necessary, you get out of these 6, 9, 18-month life cycles that we're in the middle of, and you can start getting into pushing features on a daily basis or on an hourly basis. The verifiability of the functionality is an important component of all that. And with this, networks also become tamper-proof. So if the network starts misbehaving for some reason, either unintentionally or intentionally and maliciously, this closed-loop system can identify that and start to restore the network to a known state that matches the state that the operator had predefined and is expecting of the network. So with that, I want to move on and ask Brian to step up. So Brian's going to speak first on Stratum, then we're going to talk about micro-ONOs, and then about verification. Thanks, Brian.
Thanks, Timon. So this portion of the talk is just going to talk through the data plane and why we think Stratum is good and positioned well for NG-SDN. So we'll start with the question why. And there's two main answers why we think Stratum is really well positioned for this. The first is Stratum's interfaces, models, and pipeline definition. So these interfaces, models, and pipeline definitions are built from today's SDNs, but they're optimized for NG-SDN. They enable top-down programmability using formal programming languages like protobuf, Yang, and P4 for our interfaces, models, and pipeline definitions, respectively. And they also enable hardware independence and vendor optionality. We use the same interfaces, the same models, and in some cases the same P4 programs on different targets. Secondly, Stratum's packaging and operational interfaces enable automated full lifecycle operation. We have telemetry that we provide necessary feedback back to orchestrators and the control plane to facilitate automated upgrade and rollback. We have machine-oriented and optimized operational interfaces that go far beyond what we had with SSH and expect and having to parse text, human-readable text. And we also seamlessly deploy Stratum with Docker. So let's first take a look at each of these steps in more detail. So defining the data plane, Nick and others have talked about how you can use P4 to define the parser, which means the protocol headers, as well as the forwarding tables in unambiguous code. But what happens once you write that P4 program? So we take a P4 program and we run it through something called a P4 compiler. And the first role of the compiler is to generate a control plane contract. This is called the P4 info, and it's ultimately how we will program against this contract going forward. The second role of the compiler is to allocate the resources required to realize the pipeline and hardware, as well as to generate the runtime mapping from our contract down to hardware. And today in Stratum, we use compilers for Broadcom Tomahawk and Barefoot Tofino. Next, we take that contract and give it to both the network OS as well as the switch OS. And we take the binary from the back end and give that to the switching ASIC, as well as the driver on top of the ASIC. To control our pipeline at runtime, we have a new control plane interface called P4 Runtime, which is based on gRPC and is program independent. So control apps and the controller or network OS use that to communicate with the switch. Next, we'll move on to telemetry. So all network configuration and telemetry state is modeled using programmatic definitions in Stratum. And we use the same set of industry-driven models across all Stratum switches to ensure interoperability. So we start with the open config models. We add a few extensions that are Stratum specific, and then vendors can add on top if they need. But we take these models, we run them through a Yang compiler, and we produce a protobuf representation, which is our machine-readable and binary representation of these models at runtime. These models go through a protobuf compiler, and we generate language-specific C++, Python, Java, or Go code that is ultimately going to be used by the client or the server to implement these on the device. So the models go to the switch, where we do mapping down to hardware, and the models also go to the controller, which will use these to make configuration changes as well as to read telemetry. The interface that we use to do this at runtime is called GNMI. It's an evolution you can think of netconf. We use it both for configuration and telemetry. The network OS orchestrators can use this information directly, as well as configuration or telemetry apps that are built on top of these platforms. It's model independent, so the API doesn't change when your models do, and it's also built on gRPC. Next, we'll talk about operations. So for operations, all of the operational services and RPCs in Stratum, we also model using programmatic interfaces. So we have clear definitions and semantics, as opposed to some previous techniques that are perfect for machine-driven operations, and they're critical for enabling automation. OpenConfig also defines a set of these services called GNOI. So we have protobuf definitions of these services for things like certificate management, diagnostics, file management, system, etc. We take these, we run them through our protobuf compiler, generating our C++, Java, Python, Go, etc. code. And that definition goes to the switch OS, where we implement its functionality, as well as to the network OS, which is the client that will use this functionality. Each of these services is defined in gRPC, and these are the runtime APIs we make available for operating a Stratum-based switch. Next, we'll talk a little bit about how we achieve cloud-style agility. So Stratum provides a deployment and testing framework that enable best practices in CI/CD, something we really haven't seen put into practice in most of networking today. Telemetry and end-to-end verification, which we'll hear more about later, are critical for enabling automated rollout, and in some cases rollback when there's problems. And the way that we achieve this is we start with source code. We start with source code, for example, maybe in GitHub, and we run this through a series of continuous integration steps. For example, first we compile the code, we run unit tests, we perform static analysis, we build Docker images, and then with those images, we run our conformance test suites on a target in a lab somewhere. And test vectors, which you can hear more about later today, is an example of a platform that can put a Stratum-based device under test. So once your CI tool has ran all of these steps, and you've checked all the boxes, you've got all your green lights, you may go through a number of additional steps, but eventually what will happen is you'll automate a rollout to production. This is where you deploy to your network. An orchestrator, like a Kubernetes or other cloud-based orchestrator, can take these Docker containers and roll them out to devices, then use telemetry to discover that things are working or not working. If they're working, continue the rollout. If they're not, we can roll back. And the most important thing is what this enables is an ability to iterate. So you roll this out, you find new problems, you have new features, you write more code, you run this through. And you can do this over and over again on a days or weeks time scale rather than a months to years time scale. So you may have heard that Stratum is open source this week. And I just wanted to give you a little bit of context around what to expect in the open source launch. So first of all, this is an alpha release, which means the software architecture is in place. We have support for fixed function and programmable targets, as well as a software switch. But some of the features aren't there yet. But there's still a lot that you can do with Stratum today. We've done a lot of demos over the last year on Stratum. You can see some of them today. I'll talk more about them in a little bit. It's also ready for user experimentation and for porting to new platforms. Maybe most importantly for the vendors of you in the room, our shift from a proprietary license to Apache 2.0 means that Stratum can now be incorporated into vendor products. And if you want to use Stratum or try Stratum on a box today, there are 6 different vendors that provide boxes working on 2 different silicon ASICs, Barefoot's Tofino ASIC and Broadcom's Tomahawk ASIC. We also have two software switches. One is a functional software switch that can pass packets called BMV2 or Behavioral Model V2 from the P4 community, as well as a dummy switch you can use for API testing. Going forward, we expect to see more targets from these existing vendors, as well as targets from new vendors. So we're just kind of at the beginning of Stratum. We had a community that we've built that's worked really hard to get Stratum to its open source launch. But really what is exciting about what we have ahead and what's in store. The open source launch means the community is going to expand. We're going to have new members that haven't been able to join during the private period that are going to be able to take this and run with it. We'll see new switching platforms, new switching chips, and maybe even new types of targets that aren't necessarily switches. We also expect to see hardening, testing, and support coming from vendors now that it can be incorporated into these products. And all of this is in a goal of pushing Stratum towards production. And really what we want to do in the context of Next-Generation SDN is make sure that we have a stable and production-grade data plane substrate to enable building the control planes and the telemetry analytics verification that we're going to hear about in the rest of this panel. The other thing that's happening in parallel is ONF has a set of platforms that are either currently in production trials or moving towards production. These things like Trellis, SIBA, ODTN, and OMEC are providing requirements to the Stratum project, which its community and vendors are taking to heart. And what we're seeing is what these requirements will turn into is a set of new capabilities. For example, a P4-defined data plane, an ability to do VNF offloading, an ability to do telemetry, both device state telemetry as well as in-band network telemetry, that will make these platforms richer and more powerful. If you want to see Stratum in action, we have 3 demos in the booths highlighting Stratum. The first is an interoperability demo. The 2 ASIC vendors and 6 platform vendors came together to build a IP leaf-spine fabric using 8 different hardware switches. And this demo highlights hardware independence and automated full lifecycle operation. The second demo is MicroOnos, where we're highlighting zero-touch provisioning using 3 Stratum switches. And finally, in SIBA, we're highlighting top-down programmability by offloading the user portion of the BNG used in SIBA to a Stratum-based device. So that's all I had. The next speaker will be Thomas, who's going to talk about the control plane.
Great, thank you.
Thank you.
Watch the water behind you. Didn't want you to sit on your cup.
So hi, everybody. So you've heard Timon and Brian talk about the top-down programmability and Stratum, specifically how Stratum provides hardware independence and demonstrating it via support for Broadcom as well as Tofino chips. Of course, that is exposed to the upper layers of the stack through next-generation software protocols such as top-down, which provide top-down programmability, fine-grained control, and fine-grained measurement, which is required for the next-generation capabilities. This is, of course, mined and harvested by the network operating system, which, and this is what I'm going to talk about, how the MicroOnos, the next-generation operating system, is going to provide these capabilities for zero-touch provisioning and network verifiability. Of course, the network operating system is just a platform on top of which one can develop SDN applications and solutions, which then can be orchestrated into the environment using continuous integration and continuous development. And this platform, at least from perspective of ONF, is going to be MicroOnos. So what is MicroOnos? It is a next-generation architecture of ONOS, a controller with which you're very familiar, I assume. And its aim is to provide a smooth transition from the current architecture, which is Java-based and OSGI-based, into the microsystem and cloud-native environments. We aim to extend its arsenal of operations that it can perform from not just control, but also to be able to engage in configuration, be able to operate on devices, be able to upgrade their software, deploy certificates, and perform diagnostics in order to be able to operate in a broad spectrum of production requirements. Of course, we're pivoting from OpenFlow to native support of the next generation of SDN interfaces, which includes the interfaces such as GNMI, GNOI, P4 runtime, and support for standard models such as OpenConfig. One of its aims is also to provide first-class support for fifth generation RAN edge. And with this comes strict requirements for performance, scale, and very, very strict near real-time latency requirements, guarantees. And I've already mentioned that it aims to be deployable via cloud-native deployment. So let's take a look at an example of such a deployment. You have a network with some wired and wireless devices. Clearly, one needs to be aware of what that network looks like through topology. So we need to have subsystem that keeps track of what the topology substructures. We need to have a system to be able to convey configuration operations onto the environment, to be able to operate, to upload software, update certificates. Of course, to be able to not only shape the pipeline of the data plane, but also to be able to program the behavior of the data plane. And there needs to be a subsystem to deal with specific requirements of the RAN edge, to be able to handle handovers, switching from tower to tower, and to be able to effectively use the spectrum. Of course, as microservices, these have to be reasonably stateless, and for this we need to be able to stash away the state in a resilient and performant, database, distributed database. And in order to support some legacy devices, not just a Stratum, we need to be able to have a place to adapt to other protocols. Clearly, our first objective is to support Stratum, and therefore speak natively via GNMI, GNOI, and P4 runtime. But we also need to have a layer that supports adaptation to devices that are not Stratum compliant as well. On top of this minimal core, one can then develop additional applications. Some examples include ZTP, intent subsystem, and arbitrary sets of applications. Of course, having a CLI and UI as a complement is also a must. And of course, this entire system is to be orchestrated via Kubernetes. Of course, there are many different network operations that we aim to support with this broadened set of operations that we are adding to the system. We need to be able to handle cases such as provisioning new devices and adding them to the network, be able to add new features to the existing data plane, isolating faulted network devices and redirecting traffic around them, and many more. Of course, as you'll see, a lot of these things will require the broad top-down control and intelligent and cooperative data planes such as Stratum. And of course, the next generation software interfaces make these possible. So here's an example of being able to add a new device to the network. Usually a priori, operator defines a template for what a configuration of a particular device fulfilling a role of either spine or leaf or an access device should look like. Then when ONOS either discovers or is given the address of the device as a new device to be introduced to the network, along with a role for that device, the ZTP application can then use the operation subsystem to be able to download the desired version of the switch to software via GNOI, be able to install new certificates, be able to set the desired chassis configuration. Then using P4 runtime, it prescribes what the pipeline configuration for the device should be. And then when the device is ready to be added to the network, enables the ports and marks the device as available. At this point in time, ONOS discovers the new links, verifies that they're supposed to be there, and applications can proceed to use the P4 runtime and pipeline-specific constructs to operate in the device. Another example is adding new data plane feature. Traditionally, this would require years to add new feature to the silicon, but with P4, you can have a network designer to create or modify a P4 program to introduce new headers or tables into the pipeline of a device. The P4 program is compiled into artifacts for the switch, but also artifacts for the developers of the applications. This is all assembled into an application for operational deployment via ONOS, and then the developer can use the APIs to develop the application. And once the application is ready and the entire assembly is ready to be put into production, ONOS can download the artifacts to the switch via P4 runtime, and then applications can proceed to program the pipeline using pipeline-specific constructs. So micro-ONOS, it's a replacement, or I guess we should think of it as an evolution of ONOS. I mentioned that it's broadening the set of operations that ONOS can do today. Today, ONOS primarily focuses on control, which is controlling forwarding behavior, but we're adding capabilities to be able to engage in operations and configuration. And so since those are areas where ONOS today is somewhat lacking, I guess one could say, we're focusing on those areas first. And so we're, I think I must have pushed the wrong button. So we're focusing on ONOS configuration first, and we're demonstrating on the show floor here that we can engage with multiple devices and perform multi-device operations, which can be atomically deposited to the data plane, and then can be rolled back if something doesn't go quite right. So that's where primary focus is. We're also starting to develop a next generation topology subsystem. Its API is still in progress, and just for purpose of demonstrating, to show some of the capabilities that will be possible with these new features, we've developed a demonstration ZTP application, which we'll intend to develop into full production app down the road. Of course, we're basing, just like current ONOS, we're basing all of our storage distributed state keeping in using atomics. Except we're using next generation of atomics libraries that are specifically oriented towards supporting the Golang programming language. Of course, for demonstrations, we also have UI, and then since we want the system to operate smoothly, we're using, we also developed the integration testing framework. So hopefully this is just a quick overview to tell you about what micro-ONOS is. ONOS has been and continues to support SDN capabilities. Even existing ONOS supports SDN capabilities, but to enable the broad down control of the data plane programming. But we're extending that to be able to also be able to add more breadth to the operations that you can do, to be able to configure as well as control the devices. And also to be able to do zero-touch provisioning to reduce the operator's OpEx. And as always, the performance and scale and high availability are extremely important, so we're continuing to carry that legacy forward. And overall, we just plan to carry the torch of SDN down the road with ONOS and micro-ONOS. That's all I have, and I think the next to talk about the verifiability is Nate.
So hi, it's great to be here. Figure out this quicker.
Top button.
Oh, great. So my name's Nate Foster. I'm a professor at Cornell University, so I'm not part of ONF, but I've been delighted to work with the ONF team since late spring on thinking about how verification might play a role in next generation SDN. So I thought I'd start by going back to some ancient history. Probably some of you know this paper. That's by David Clark, who is one of the chief designers of the DARPA Internet. And towards the end of this paper, he actually talks about verification and other design aids, and has a somewhat pessimistic view of the kinds of tools that the formal methods community had available in the mid-'80s. And there's this quote where he says, while tools to verify logical correctness are useful, both at the spec and implementation stage, they don't help with the severe problems that often arise related to performance. And he saw these kind of performance-oriented issues like congestion or failures, resilience, as the key issue for having a network achieve its goals. And so the conclusion is that we should focus on those problems and less on kind of traditional logical formal methods approaches. But if you fast forward to 2019, there's a lot of action in network verification. There's startups. Some of the larger companies have acquired these startups. And you see the cloud providers who have teams internally that are looking at how to use different kinds of verification tools to improve the reliability of their infrastructure and also to increase the speed of their innovation. So I think what's changed is that, first of all, networks have grown immensely, of course, since the early days of the internet. And so someone who's operating a huge cloud infrastructure has to deal with issues that related to how they configure all these thousands of devices that maybe were less of a concern in the old days. The other driver, I think, is, of course, we have these new architectures. So SDN, things like P4, give us models of what the network is doing that look more like software. So we can start to think about them more like we do with ordinary programs. Another thing that's happened that's kind of a driver is that the formal methods community has made immense progress in the 30 years since Clark wrote his paper. There's a lot of new techniques for modeling complex systems, hardware and software systems, and there's highly scalable automated tools now that can solve problems automatically. So SAT and SMT solvers are kind of driving a wave of innovation in all areas of computer science. And so I think it's interesting to sort of reconsider how we could build networks that have verifiability built in, and that might help us be bolder in terms of what we ask them to do and also do a better job at achieving those goals. The sort of key technology that I'm interested in my own work, and I think is playing a key role in the ONF platforms, is the idea of having a way of specifying the interface and sort of a contract between the control plane and the data plane. So no matter what you're using upstairs and no matter what you're using downstairs, there's going to be some place where we specify what we're asking the network to do, and P4 can play that role. So sort of viewed bottom up, you can see P4 as a language where we're giving a precise, clear description of how the network processes packets at any moment in time. And then, of course, going down, if you have a controller like ONOS or Stratum, you can actually specify what you want the network to do. And that might mean building new kinds of packet processing functionality, adding telemetry, and so on. And so P4 kind of sits in the middle, and it's a really nice vehicle for thinking about how we could increase the assurance of networks by using verification technologies. So let me step back and just take a very broad view of verification. There's a nice characterization that one of my colleagues at Cornell came up with in a paper about 10 years ago, looking at verification in the operating system context. And broadly speaking, I think there's kind of three ways you can gain assurance in a system. So the first is sort of by fiat or by construction. Right? You can sort of just engineer the very structure of the system so that certain properties hold. And I'll show you an example of this in a second. The second technique is by analyzing. So if you have maybe a program that describes the system you're trying to verify, you might be able to use maybe the semantics of that program to prove some properties or to establish some properties that you care about. And the third way is by what I'll call synthesis. So maybe you don't want to analyze the system, but you have a way to instrument it and collect evidence about what it's doing. You might be able to use that evidence, say runtime telemetry data, in order to check that the system's behaving as you'd expect. So let's kind of go through these and consider the roles they might play in SDN. So I think for construction, there's lots of examples of this, but the one that kind of exemplifies sort of correctness by construction or assurance by construction for me is something we've seen a lot of, namely network virtualization. So this shift to virtual networks has allowed people building networks to endow them with structure, things like segmenting different parts of the network, even microsegmentation, where we're really at fine granularities controlling the structure and communication of the network. And that lets us get away from things like firewalls and sort of defending a perimeter. We're sort of shaping the infrastructure to have certain properties so that certain kinds of faults, like breakages of isolation, can't happen. So construction is a really powerful technique. We should continue using it. And it's also uniquely enabled by the ability to sort of program the network and change its structure. But there's more we can do. So as an example of analysis, there's some work that I did a couple years ago with folks at Barefoot Networks, where we ask the question, if you have a P4 description of a forwarding plane, could you automatically, or mostly automatically, check that it has certain properties? And I'll show you a little example in the next slide. But the basic idea is that we're going to build a nearly fully automated tool where you feed in your program, and you feed in a property that you want that program to have, and then you get out an answer, yes, your program has this property, or a counterexample if it doesn't. The way this works is really exploiting this idea that SDN and P4 kind of view networks just as special kinds of programs, and so we can use all the body of work from the software community on reasoning about the behavior of programs to start reasoning about networks as well. So we have a fairly standard pipeline that sort of takes our P4 program, takes our property, and massages it into a logical formula that we can then ship off to a solver, which very efficiently can give us an answer. So just an example to illustrate this, you might have a device that's supposed to be involved in enforcing some kind of network-wide isolation policy, and perhaps internally the device uses some specific kinds of packet processing functions like network address translation or an access control list. Anyone who's had to implement these kinds of functions will know that the order that you do these things matters. There's a very nice blog post from my friends at Forward Networks that sort of explains the things that can go wrong if you get this backwards. And essentially, it has to do with the fact that the access control list is basically dropping certain kinds of packets by matching their headers, but the network address translation unit is actually changing those headers. So you need to express the access control sort of either pre or post address translation, or you get the wrong behavior. And here's a little video I have that demos P4V kind of checking this kind of property on a simple example. So for those of you who've seen P4, this will be familiar. We just start by defining the headers that this small program is going to deal with, a parser for those headers, and then the actions that are involved in access control and network address translation. So either allow the packet or drop it, and then rewrite it or do nothing. And for the sake of the example, this program just does those two things. First, access control, and then address translation. And the little annotation that I have here is just a simple example to show that we might care that maybe certain addresses, packets coming from certain addresses are dropped. So we can use P4V on this program to check if that property holds, and we see that it doesn't. And the reason, of course, is that our tables might be empty. And so in general, when you're verifying a data plane using analysis, you also need to know things about the control plane. So our tool also allows you to specify assumptions about the control plane. In this case, I'm just going to say that the control plane has a rule that drops the packets I care about. More generally, it could be some symbolic constraints on the control plane. And now this is enough to verify that the program indeed drops those packets. And interestingly, if we swap the order of these tables, which is the bug that's discussed in that Forward Networks post, we see that actually we again get a bug, and we get a counterexample because the address that we're trying to drop actually gets rewritten by the network address translation, and so it then passes the ACL. So this is just a very quick, probably two whirlwind view of how you can use analysis to gain assurance about a programmable forwarding plane. And the last thing I want to say is that synthesis also has a key role to play. This is a slide that Nick showed yesterday in his keynote, and it shows how telemetry and runtime verification can be used to check for properties. So just to review in case you weren't there, the idea is that by exploiting the programmability at the forwarding plane level, we can actually add to packets very detailed information about what happened to them as they went through the network. This is really unprecedented to be able to do this kind of monitoring. And so, for example, we might keep track of things like the queuing delay experienced at each hop, as well as other characteristics like what rules were used, what switches were traversed. And then at the end, we can strip off this record, which now tells us exactly what happened to this packet and all the state that was experienced going through the network, and use that to verify at runtime that certain properties hold. And I think this is interesting for a few reasons. First of all, it's very cheap in terms of upfront costs. There's some, of course, runtime costs and overheads to doing this, but it doesn't require you to go get a PhD in logic or start using a theorem prover. It's just sort of collecting information at fine granularity about the behavior, and then checking that the data you've collected doesn't illustrate some fault. The other thing I think is great about this is it actually, in part, I think rebuts Clark's worry about verification, because here we actually are keeping track of things that involve performance. So it's not complete verification of performance properties, but it is telling us about things like congestion, which historically have been very difficult to reason about with analytical techniques. So So I think there's a great opportunity here to use runtime verification to check performance properties. Okay, so just to sum up, I think that we're on the verge of a really exciting transformation as a lot of these technologies that have been sort of incubating for decades can be applied to networks. And there's lots of interesting challenges. I think we're early days. So finding ways to use these different capabilities we have to enforce application level or network-wide properties. Quantitative verification, I think Clark was right. You know, the things we really care about is that the network works, that we don't have performance-oriented faults. And then, of course, scaling up to very large networks is always a challenge. And so there's probably some great engineering work to be done on making that possible. Okay, thanks.
Good, thanks, Nate. Okay, so we've covered a lot of ground. And I wanted to take just 2 minutes at the end here to try to wrap it back together and put it in the context of everything else you're hearing this week. I know there's a lot going on, a lot of different moving parts at ONF and our broader community. And you know, Next-Gen SDN is a really important and vital part of that. And one way to think of it, this is a diagram that some of you may have seen that tries to sum up very simply the sort of the lineage of ONF, starting with SDN and OpenFlow, and then to the controller and to the Cord project. And over the last year plus, the Cord project has expanded, and there are a whole bunch of sub-projects you might think of them as, SIBA and all the way down to Trellis. You've been hearing about these all week. I won't go to them in great detail, but they're all part of the Cord umbrella and the platforms that we're delivering as we move forward. So this whole Next-Gen SDN effort is really taking a look at retooling the underpinnings of this whole movement and everything that we've been working on, both SDN and OpenFlow. And now today you've heard about MicroOnos running on top of Stratum, and then the verification engine that kind of creates a closed-loop control all around that. And the point to make here and to understand is that the Next-Gen SDN work that we've talked about today is the new underpinnings, the new substrate for all of the platform work, the Cord-related work that's also ongoing in parallel at ONF. And the beauty here is that all the platform work is seamlessly able to migrate to the Next-Gen SDN platform and then leverage and take advantage of all the new capabilities. And this has already been demonstrated even some time ago. I don't remember how long, maybe last spring, where Trellis was shown running on top of both OpenFlow switches and Stratum switches, side by side simultaneously. And you're going to see things like SIBA being able to run on top of Next-Gen SDN and push BNG functionality all the way down into the silicon, thereby accelerating the operation of the whole SIBA pod and deployment. So this is really an exciting roadmap. There's some beauty in the fact that these two areas can progress simultaneously and in parallel, and the smooth migration that's being provided really makes this seamless in many ways and very easy for us to progress very, very rapidly. So, revolutionary new capabilities. And there are quite a lot going on here. The programmability of the forwarding, both a full tool chain, not just the silicon, the microservice level lifecycle components, hardware independence, and the network verification. And all of this rolls up into really transformational benefits. For the first time, operators can begin to really own their own network and control the network top down. It enables a level of rapid network innovation that we've never seen before, zero-touch operations and getting the human out of the way as we're running our networks and as we scale. And lastly, but really not leastly, a robust hardware ecosystem where operators can take the latest silicon and the latest white boxes and put them in their network rapidly rather than going through 6-9 month deployment cycles. And in this way, operators can leverage the latest technologies really, really rapidly, but also vendors and component suppliers can get access to the network and can bring components forward, and operators can try them fast and deploy them fast. So there's one more thing I learned this week. So, a lot going on, a lot of moving parts, and even just a lot just in this one session. But according to Nick, it sounds like apparently, after we deliver all of this, we're all going to be at the beach drinking a lot of pina coladas. So for those of you that missed Nick's talk, I really encourage you to check out the video link. It's already up and live. That talk really talks about a lot of the background that leads to a lot of the work that you see here today. It's really exciting to see it all come together. And I want to thank the panelists. So please, yes.